Have you ever wondered where physics draws a hard line not for matter, but for escape itself? The event horizon is that boundary. It's the surface around a black hole where gravity is so strong that even light can't get out. From far away, a falling clock appears to slow and fade. For the traveler, crossing can feel ordinary in general relativity. No alarms, just a one-way path inward. Tidal forces depend on mass. Near a supermassive black hole, they can be gentle at the horizon, while smaller ones tear objects apart much earlier. What becomes of light, information, and time there? Hawking radiation, entropy, and the information paradox all meet at this edge. If clear, calm science is your pace, a quick like and subscribe helps others find it. Settle in, let's map the point of no return. The event horizon is our focus. It is a region where familiar rules begin to bend, then stop giving useful answers. Even light, the fastest signal in nature, cannot get out once it crosses that boundary. The phrase, point of no return, is not drama. It is a simple description. Outside the boundary, paths can curve away or around. Inside it, every path points inward. Picture space around a black hole as calm but not empty. Nothing shines from the hole itself, yet its presence is clear from what it does to nearby light and matter. Far away, the usual predictions still work. Gravity shapes orbits, clocks tick at normal rates, distances feel ordinary. As you go closer, the predictions remain lawful but grow unfamiliar. Starlight bends more than expected. Time seems to slow for anything deep in the gravitational well. Distances measured along certain directions stretch in ways that are not obvious to our eyes. The event horizon is not a physical surface. There is nothing to touch. It is a mathematically defined boundary in space-time. At that exact radius, the escape velocity equals the speed of light. Escape velocity means the minimum speed needed to climb out of a gravity well and never fall back. For Earth, it is about 11 kilometers per second. For a neutron star, it is a significant fraction of light speed. For a black hole at the horizon, it equals light speed itself. Since nothing can move faster than light, nothing can escape once inside. For a spacecraft or an astronaut, crossing the horizon marks a simple change in possibilities. Outside, many futures are open. You can turn, hover for a while with enough fuel, or leave on a carefully planned trajectory. Inside, all future paths end closer to the center. Thrust is no longer a meaningful tool. No engine can push a path that space-time will not allow. This is not about poor piloting. It is about geometry. In the simplest case, a non-rotating, perfectly spherical black hole, the event horizon is a sphere. Its size depends only on mass. This case is described by the Schwarzschild solution to Einstein's equations found during World War I by Karl Schwarzschild. His work shows that compressing enough mass into a small enough region curves space-time so strongly that a horizon forms at a radius we now call the Schwarzschild radius. For an object with the mass of our Sun, that radius is about 3 kilometers. For a supermassive black hole, millions or billions of solar masses, the horizon can be millions of kilometers across. Rotation and charge modify the exact shape and behavior, but mass sets the basic scale. Despite its importance, crossing the horizon would not feel dramatic for an observer falling into a large black hole. There is no flash, no impact, no sound. Locally, free fall feels like weightlessness. If the black hole is supermassive, the tidal forces at the horizon can be small enough that a person might not notice them immediately. The difference appears for a distant observer watching the fall. That observer would see the infaller slow down as they approach the horizon. Signals would take longer to arrive. Light from the infaller would be stretched to redder wavelengths by gravity, fading until it becomes undetectable. From far away, the crossing appears to take an infinite time. From the infaller's own point of view, it happens in finite time and without fanfare. Both descriptions are correct within general relativity, because gravity affects time itself. This difference in viewpoints is a key lesson of the event horizon. Gravity is not only a force, it is the shape of space-time. Time flows at different rates in different gravitational fields. Clocks deep in a gravity well tick more slowly than clocks far from massive bodies. The effect is small near Earth, but becomes extreme near a black hole. That is why never crosses and crosses quietly can both be true, depending on who is measuring. What lies inside the horizon is largely unknown to us because information cannot get out. This is not a matter of poor instruments. It is a causal block. Outward signals cannot reach the exterior. The center, often called the singularity in the simplest models, is where the mathematics predicts infinite curvature. Most physicists see that as a sign that our current theories are incomplete at such extremes. A full description may require quantum gravity, a theory that unifies general relativity with quantum mechanics. Many ideas exist, but no final answer has been confirmed by observation. Even without access to the interior, the horizon affects what we can observe. It sets a meaningful size for the black hole. It limits the region where stable orbits can exist. Just outside the horizon, material can circle at very high speeds. In many systems, gas falling toward the hole forms an accretion disk. Friction and compression in that disk heat the gas to immense temperatures, producing X-rays and other high-energy radiation. The black hole stays dark. The disk shines. In some galaxies, the disk and related jets outshine the combined light of billions of stars. Light paths near a black hole curve strongly. This gravitational lensing lets us see parts of the disk that would normally be hidden behind the hole. The far side appears bent into view. The result is a distinctive photon ring and a dark region often called the shadow. The shadow is not the horizon itself, but its size and shape are closely tied to the mass and spin of the hole. The Event Horizon Telescope, an array of radio telescopes spread across Earth, uses very long baseline interferometry to resolve these features. Its images of the supermassive black holes in M87 and in the center of our galaxy are landmark results because they show the silhouette carved into the glowing material just outside the horizon and match what general relativity predicts for such environments. Understanding the horizon also means understanding how black holes form. Nature does not place signs in space. It follows processes. Many black holes begin when massive stars run out of nuclear fuel. Without pressure from fusion to support the core, gravity wins. The core collapses. If the mass is high enough, no known force can stop the collapse, and a horizon forms. Black holes can also grow by merging with others, or by steadily feeding on gas and stars drawn in by gravity. Over billions of years, central black holes in galaxies can reach enormous masses. The pull of a black hole is not magical or unusually aggressive. If our sun were instantly replaced by a black hole of the same mass, Earth and the other planets would continue their orbits almost exactly as before. Daylight would be gone, but orbital paths would remain because the gravitational field at our distance depends on total mass, not on whether that mass is a star or a black hole. The difference appears only when objects move close to the horizon. There, the geometry forces inward motion, and escape becomes impossible. The invitation of a black hole is gradual. As a small body orbits, friction with other matter or gravitational interactions can cause energy loss. Paths slowly shrink. Gas spirals inward, making a disk. In the outer disk, orbital speeds are a meaningful fraction of light speed. Closer in, they reach even higher fractions. At these speeds, collisions and compression heat the gas. Radiation carries away energy, letting the gas sink further. The final stable orbit outside a non-rotating black hole, the innermost stable circular orbit, marks the inner edge of long-lived orbits in the simplest model. Inside that region, spiraling continues quickly toward the horizon. Observations of X-ray binaries, systems where a black hole or neutron star pulls gas from a companion star, reveal many of these effects. The spectrum and variability of the X-ray light tell us about the temperature and motion in the inner disk. In distant galaxies, active nuclei powered by supermassive black holes show similar physics on larger scales. Jets launched near the disk can extend for thousands of light years, guided by magnetic fields and the spin of the hole. These jets are not proof that material escapes from inside the horizon. They form outside it, where energy can still flow outward. The concept of escape velocity brings the horizon down to a familiar idea. On Earth, a rocket needs a specific speed to break free from gravity. With enough fuel and the right path, it can leave. Near a black hole, no amount of fuel helps inside the horizon, because away is not a direction the geometry allows. That is the essence of the no-return phrase. It is not a warning in words. It is a statement about the shape of space-time. Black holes are common on cosmic scales. Stellar mass black holes come from single stars that were heavy enough at birth. Intermediate mass black holes may form through repeated mergers in dense clusters, though their origin is still under study. Supermassive black holes sit in the centers of most large galaxies, including our own. Their horizons are large, and their tidal forces at the boundary can be mild. This is why falling into a supermassive black hole does not require being torn apart at the edge. The danger grows after crossing, where stronger tides appear as the radius decreases. The horizon also touches deep questions about information. If nothing escapes, what happens to the information about the matter that fell in? Stephen Hawking showed that quantum effects allow black holes to radiate slowly, a process now called Hawking radiation. In classical relativity, black holes only absorb with quantum fields in curved space-time. They can emit. The radiation is extremely weak for large black holes, so we do not observe it directly in astrophysical systems, but the idea leads to an information paradox. Does the radiation carry information about what fell in, or does the information get lost? Many proposals aim to resolve this tension, from subtle correlations in the radiation to new structures near the horizon. The discussion is active and technical. What matters here is that the horizon forces us to test our ideas about how physics stores and moves information. Rotation changes details, but not the central role of the horizon. A spinning black hole, described by the Kerr solution, has an ergosphere outside the event horizon, where spacetime is dragged around by rotation. In that region, energy extraction is possible in principle, and the inner edge of the disk can sit closer to the horizon than in the non-rotating case. Spin affects the size of the shadow and the location of the last stable orbits. When observers analyze light curves and spectra from accretion disks, they often fit models that include spin as a key parameter. Because the horizon is invisible, we confirm its presence by its effects. We measure how stars orbit around dark masses. We track how gas speeds up and heats as it draws near. We map the ring of lensed light surrounding the central dark region. We compare these signatures to the predictions of general relativity. So far, the matches are strong. Limits on alternatives like extremely compact stars without horizons grow tighter as instruments improve. The better the agreement, the more confidence we have that the event horizon is real and behaves as theory says. It helps to separate cause from appearance. A black hole does not actively reach out to pull more than any mass would. It shapes space-time. Objects follow the allowed paths in that shape. When an object gets too close, the allowed future paths all head inward. This clarity removes drama and leaves a clean rule. The horizon marks where outward futures end. In daily terms, gravity curves both space and time. Near Earth, GPS satellites must correct for this because their clocks run slightly faster than clocks on the ground. The same theory that explains that small shift also explains the extreme shifts near a black hole. The framework is continuous. Mild effects for weak fields, strong effects for strong fields. The horizon sits at the far end of that continuum. In quiet systems, a black hole can sit for ages, almost invisible. If little matter is nearby, there is little light. Only when gas or stars draw near does the system brighten. During a feeding episode, the signals are rich with information. Variations in brightness trace orbital periods. Spectral lines broaden because material moves at high speeds, a relativistic effect. Timing features can hint at the structure of the inner disk and the mass of the central object. Each piece of data fills in part of the picture, like careful brushstrokes on a dark background. None of this requires special effects language. The event horizon is a boundary set by a speed limit and by geometry. The interior is cut off not by walls, but by causal structure. The exterior speaks through light that almost did not escape light, bent, delayed, and redshifted by the deep well. The more precisely we measure those signals, the more sharply the boundary stands out in our models. In summary form, but without concluding here, the key points stand together. A horizon forms when mass is compressed enough to make escape impossible for light. Crossing it is uneventful for the traveler, but appears to freeze and fade for the distant observer, because time is shaped by gravity. The horizon gives black holes a measurable size, sets the stage for fast orbits and hot disks, and ties into open questions about information and quantum effects. Black holes are not vacuum cleaners. They are regions where space-time leaves no outward roads. Consider how this changes our sense of place. An event horizon is not just a location you can mark with a flag. It is a boundary in the fabric that tells objects which futures are available. Cross it, and every possible future points inward. The geometry does not ask what you are or how hard you try. It simply carries you along. The closer you are to such a boundary, the more the ordinary rules of perspective, time, and distance begin to change. As vision narrows near a black hole, time does not keep the same pace, and straight lines stop behaving like straight lines. The pull we call gravity becomes more than a familiar tug. It shapes what can be seen and what must stay hidden. This is where physics we test every day meets open questions we have not answered. The event horizon is not only the boundary of a black hole, it is the edge of what present theories can safely describe, and just beyond it our models struggle. Gravity on Earth feels steady and kind. It holds oceans in their basins and keeps your body anchored to the ground. Around the sun, it acts like a careful bookkeeper, balancing the fall of the planets with their forward motion so orbits hold. Near a black hole, nothing about the law changes. but its logic runs to an extreme. Past a certain distance from the center, there is no longer a balance to keep. The pull does not merely keep you close, it carries you inward and does not return what it takes. Gravity has no will, no hunger, yet it never flips direction, never turns off, and never saturates. You can block light with a wall and muffle sound with insulation. There is no shield for gravity. Its strength weakens with distance but never quite goes to zero, and in a black hole the same rule is driven toward an absolute. What makes a black hole so different is not the field far away, but the concentration of mass. With planets and stars, you cannot get near enough to the center for gravity to become overwhelming. Solid surfaces or pressure-stiff interiors stand in the way. Even a neutron star, with its intense density, spreads its mass over a measurable radius. A black hole packs mass into a region so small that our present theories cannot resolve the final interior. That compactness lets you approach far closer to the center than any other object allows, and close in, the extremes appear. Falling towards such an object would not feel like a yank on a rope. Free fall is smooth. The sense of being pulled comes from the path that space-time allows, not from a hook grabbing you. If the hole is large, the change in gravity from head to toe, the tidal force, can be mild at first. You might notice nothing unusual as you drift. Deeper in, the difference in pull between near side and far side grows. In smaller black holes, the change becomes sharp much earlier, stretching along one direction and squeezing along the others. The nickname for this, spaghettification, is colorful, but the idea is simple. Tides act unevenly across your body. On Earth, falling ends with a surface. A ball strikes the ground. A meteor meets thick air. A black hole offers no landing. Even before the horizon, space is curved so strongly that climbing back out demands enormous energy. The closer you are, the more you need. Exactly at the horizon, escaping would require the speed of light, straight outward, and then some, which nature does not allow. Light is the fastest messenger, and even it cannot win once across the line. A picture can help. Imagine a hill, far away. The slope is gentle. Walking outward is easy. As you move toward the center, the slope steepens. You must work harder to climb. At the horizon, the hill turns into a vertical drop. There is no path that rises out. Inside, even pointing uphill does not matter. Every direction you choose still guides you downward. This is geometry, not a hidden force switching on. Gravity creates a shape of space-time in which all future roads tilt inward once you are too close. This does not mean black holes eat quickly. A black hole without material nearby stays dim and quiet for long stretches of time. But when gas or stars come close, the change is dramatic. In falling inward, matter sheds gravitational energy. Collisions and compression heat it. It glows in visible light, ultraviolet, and especially in X-rays and gamma rays. All that light comes from the material still outside the horizon. Cross the boundary, and the signal is cut off. In active galaxies, where supplies of gas are steady, the output may rise and fall in chaotic patterns as clumps collide. Magnetic fields thread the hot plasma. In some cases, twisted fields and rotation launch jets narrow beams of particles pushed to speeds near light that shoot along the spin axis. These beams can travel for thousands of light years and change how gas cools and forms new stars, so the central object affects regions far beyond its immediate edge. Smaller systems show the same story on a tighter scale. A stellar mass black hole in a binary can draw gas from a companion star. The gas flattens into a glowing disk, and, when feeding flares, the X-rays brighten across large distances. These flares are a clear signature of gravity doing work on matter, turning rest mass into radiation with an efficiency that beats any engine we have built. Through all of this, the black hole keeps a simple identity. It has no surface to wear down, no crust to chip away. What falls in adds to its mass, making the event horizon larger and the gravitational reach longer. The activity, the noise, the light, the turbulence belongs to the space outside the horizon. The object itself remains bare in a specific sense. According to the no-hair idea, a settled black hole is described from the outside by just a few numbers: its mass, its electric charge, and its spin. The complicated details of what went in star shape, rock chemistry, cloud structure do not matter to the exterior fields. Gravity and electromagnetism read only those few parameters. This uniformity gives the horizon its sharp character. From the outside, history's inside are not accessible. That fact opens deep questions about whether and how information is preserved in fundamental physics. But even without the quantum debate, the classical picture already sets a clear rule. Growth has no internal stop button. As long as matter and energy drift near enough, the whole will gain mass. The only limit is the supply. Galaxies are busy places, so supplies are common. Gas clouds wander, stars scatter. Dwarf galaxies merge into larger ones, and their central black holes can eventually merge too, settling into a bigger one with a larger horizon. Even away from the hub of a galaxy, a lone black hole can meet stray material after long, quiet spells. Every massive object has a kind of gravitational appetite. Planets gather moons, stars gather planets, clusters gather stars. But black holes are unique because there is no appeal after the crossing. Inside the horizon, there is no route back, and that certainty is part of what makes this boundary so important. Do not imagine every crossing as violent. For a supermassive black hole millions to billions of solar masses, the tidal forces at the horizon can be gentle. You, your ship, and your instruments could remain intact for a while as you pass through. The destructive stretch comes later, deeper in where the curvature grows. The inevitability, not the speed, sets the tone. You might fall slowly by using engines to delay the plunge, or quickly by freefall, but the end point is fixed by the shape of space-time. A distant observer would watch a different story. Your signals would take longer to arrive and would shift to redder wavelengths. Your motions would seem to slow to a crawl as you approached the boundary. In that view, you would never quite cross. You would fade at the edge. Both views are right in their frames. Gravity changes the rate of time, so descriptions depend on where you stand. The phrase black hole can suggest a hole in space, a pit with walls. The reality is stranger and cleaner. What exists is a region where every possible future path points inward. A trap is a fair word, but there are no physical bars. The mechanism is the layout of space-time itself. Far away from any mass, space is close to flat, and light flows in nearly straight lines. Closer in, paths curve. For ordinary objects, that curvature never forces all roads to end at the center. Orbits and escapes remain possible. For a black hole, the curvature crosses a limit. Inside a certain radius, there are no outward paths left. For non-rotating holes, this radius grows directly with mass. Double the mass, double the radius. The simplest picture has two key places: the event horizon and the singularity at the core. The real environment has richer structure in between and around these features. If you could map the gravitational landscape while moving inward from far away, a striking zone appears before the horizon, the photon sphere. At this distance, 1.5 times the Schwarzschild radius for a non-rotating black hole light can orbit in a circle. These orbits are not restful. A tiny nudge sends the photon outward to escape or inward to fall. Still, the existence of this sphere shows how strong the curvature has become. Even the fastest thing in the universe can be held on a closed track. Closer in sits the event horizon. Some people picture it as a thin membrane. A better image is the edge of a deep funnel cut into space-time diagrams. Outside the edge, some paths still climb away. On the edge, none do. Crossing does not feel like hitting a surface. The space you move through changes what outward means. Point your engines up and fire at full power if you like. The geometry still carries you inward. Inside the horizon, the structure of possible motion changes in a way our common sense resists. In normal conditions, you choose directions: forward, back, left, right, up, down. Inside the horizon, the coordinate that measures distance to the center acts more like time. The inward direction is as compulsory as tomorrow. You cannot decide to stop moving forward in time. You cannot decide to stop moving toward the core. This is not a trick of words, but a direct result of Einstein's equations written for this environment. Gravity becomes geometry, and geometry sets what can means. The singularity is the classical end of the path. In the simplest models, it is the place where curvature grows without bound and our equations blow up. That blow-up is a signal that the theory is being asked to do more than it can. We do not yet have a complete quantum theory of gravity to describe what really happens in the deepest interior. From the outside view, though, every world line that crosses the horizon ends at that center in finite proper time. The interior is truly a terminus. Rotation adds new layers. A spinning black hole drags space-time around with it, a feature called frame dragging. This swirl creates an outer region called the ergosphere, shaped like a squashed sphere that bulges at the equator. The ergosphere lies outside the event horizon. In that zone, you cannot stand still with respect to the distant stars. Space-time itself is being carried around, and you must go with the flow. Yet escape from the ergosphere is still possible. The region is interesting because it allows, in principle, energy extraction from the hole's rotation. In the Penrose process, an object entering the ergosphere can split so that one piece falls in while the other flies out with more energy than the original had. The extra energy is borrowed from the hole's spin, not created from nothing. Around and beyond these structures is the domain where gravity dominates but does not yet control every outcome. Here, accretion disks form if there is a supply of gas. The disks are thin compared to their width and extremely hot. Magnetic fields thread through them. Turbulence stirs them. Radiation carries energy outward so material can lose orbital energy and spiral inward. This is the part we can observe most directly. Before matter passes the horizon, it still talks to the rest of the universe through light and particles. In some systems, the disk, fields, and rotation together drive those long jets that sculpt their host galaxies far beyond the central light. At the precise location of the event horizon, the standard picture places no matter at all. The horizon is not a shell or film. It is a boundary in space-time, a causal edge defined by the paths light and particles can take. You could cross it without bumping into anything solid and without a sudden physical signal, unless the black hole is small enough for the tidal forces to be extreme right there. To someone watching from far away, the crossing never appears to happen. They would see you approach the boundary more and more slowly, the light you send stretching to longer wavelengths until it slips past the reach of their detectors. That fading is not a camera trick. It is baked into how light climbs out of a deep gravitational well. The inside view tells a different, but equally valid story. In your own frame, clocks tick normally, and the crossing occurs in a finite time. Space and time have been reshaped so that outward no longer connects to the future. Two descriptions, both correct within their frames, refuse to line up. Black holes force us to accept that reality can present two faces at once, separated not by opinion, but by geometry. Each layer of the system plays a role. The photon sphere marks the distance where light can loop in fragile circles. The event horizon sets the point beyond which all paths turn inward. The singularity, in the classical picture, is the interior end of every world line that passes the horizon. A rotating black hole adds an ergosphere, a region where space-time is dragged around by spin and standing still is impossible. Around these, accretion flows, and sometimes jets, tell the wider universe that something compact and heavy sits at the center. Some parts of this structure are seen through their effect on light and matter. Others are boundaries defined by the mathematics of general relativity. Together, they make a consistent map of how an object can hide absolutely and yet leave a bold signature through what happens just outside its edge. Seeing this structure as natural, not magical matters. The event horizon is what gravity produces when mass is packed tightly enough, and the same laws that keep planets in orbit are pushed to their limit. Nothing new has to be invented. Increase concentration, steepen curvature, and a one-way funnel forms in space-time. The anatomy follows from the same principles that guide spacecraft through our solar system. Only the scale and the compression change. It took time for this view to earn trust. Today, we speak with confidence because data back the models. Images of shadows, orbits of stars, near invisible masses, and ripples in space-time from mergers. But for many years, black holes lived mostly on paper. They grew out of questions that predate relativity. In 1783, John Michell, working within Newton's gravity, pointed out that a star could be so massive and compact that its escape velocity would exceed the speed of light, making it dark to distant eyes. Around the same era, Pierre-Simon Laplace independently described a similar idea. These dark stars were interesting thought experiments, but physics at the time had no reason to expect such densities in nature, and light was being reframed as a wave, not a stream of massive particles. The idea faded. General relativity in 1915 rebuilt gravity as geometry. Soon after, Karl Schwarzschild found an exact solution that describes the space-time outside a spherical mass. His result revealed a critical radius, the Schwarzschild radius, where curvature becomes so strong that outward paths for light vanish. Whether nature would ever reach such a state remained an open question. Many assumed that real stars would avoid it. The central singularity signaled the breakdown of equations, and it was easy to dismiss the extreme interior as unphysical. The fate of massive stars began to change the conversation. In the 1,930 seconds, Subramanian Chandrasekhar quantified how electron degeneracy pressure supports white dwarfs and showed there is a limit, about 1.4 times the Sun's mass, beyond which this support fails. Above that mass, continued collapse seemed unavoidable unless another pressure source intervened. The claim faced criticism, most famously from Arthur Eddington, who believed nature would prevent such collapse. Yet the math was sound, and further work on neutron stars and stellar death kept pointing toward paths that could end in horizons. By the 1960 seconds, theory and observation started to converge. Roger Penrose proved that once a trapped surface forms where light is forced inward, collapse to a singularity follows under reasonable conditions. If general relativity is right, John Wheeler helped shape the language and intuition of the field, and Stephen Hawking explored the deep links between horizons, thermodynamics, and quantum effects. Meanwhile, new instruments opened windows on the high-energy sky. Radio surveys, X-ray detectors, and precise optical measurements uncovered sources that exceeded ordinary explanations. Cygnus X1 emerged as a strong case, a bright star orbiting a massive, unseen companion, too heavy to be a neutron star. The simplest answer was a black hole. The term black hole, popularized by Wheeler, gave a clear name to the concept and moved it from the margins toward the center of astrophysics. The following decades filled in the environment around horizons. Accretion disks explained bright, variable X-ray sources in binary systems. Jets originating near compact objects illuminated intergalactic space. The idea that most large galaxies host supermassive black holes at their centers gained ground as astronomers mapped the motions of stars and gas near galactic nuclei. Quasars distant, brilliant beacons fit naturally as accreting supermassive black holes at great cosmic distances. By the late 20th century, the evidence had stacked up. The Hubble Space Telescope and other observatories found tight relationships between bulge properties of galaxies and the masses of their central black holes. In our Milky Way, careful tracking of stellar orbits around Sagittarius A times pointed to a compact object millions of times the Sun's mass in a region smaller than our solar system. In the 21st century, two landmark achievements strengthened the case further. LIGO detected gravitational waves from pairs of black holes spiraling together and merging, with signals that matched predictions from general relativity. The Event Horizon Telescope produced images showing a bright ring encircling a dark interior for M 87 times, and later Sagittarius A asterisk, consistent with light bending around a compact object with a horizon. With these results, the horizon moved from abstraction to measurable feature. This history shows how science often proceeds. Guesses become frameworks. Frameworks recruit data. Data refine or replace ideas. From Michel's letter to modern interferometers spread across Earth, the thread is curiosity about what gravity does when taken to extremes. Now, rather than asking, do black holes exist, we ask what their properties teach us about space-time and matter under conditions that no laboratory can replicate. The horizon, once described only in equations, can be probed indirectly by watching stars swing around invisible centers, by measuring the hot glow of gas that almost fails to escape, and by decoding patterns in radiation produced at the brink. Light is our main messenger across space. In a vacuum, it travels along the straightest possible paths. Near mass, those paths curve because space-time curves. This bending gravitational lensing shows up even for galaxies and clusters, not just black holes. Far from a black hole, the effect is subtle. A background star may shift slightly or appear as a faint arc. Closer in, the bending grows dramatic. The photon sphere, at 1.5 Schwarzschild radii for a non-rotating case, marks where light can loop in circles. Those orbits are unstable. The smallest nudge changes the outcome, sending the photon out to infinity or down toward the horizon. Still, the existence of circular light paths tells us how strong the curvature has become. These optical effects shape what we see. If a bright disk surrounds a black hole, the near side is obvious, but gravity also bends light from the far side, over the top and bottom, into view. The result is a warped, stacked image where multiple routes bring photons to the observer. Simulations reproduce this pattern: a bright, lensed ring and a darker interior, sometimes called the shadow. The shadow is not the horizon, but its size and shape reflect the mass and spin of the central object and the geometry of the light paths close to it. As emission comes from deeper and deeper in the potential well, two things happen to the signal that reaches a distant telescope. First, gravitational redshift stretches its wavelength because photons lose energy while climbing out. Visible light can slip into infrared and then beyond, out of range for a given detector. Second, time dilation changes the rate at which those photons arrive. A distant observer sees the clock of the infalling source run slow, the gaps between successive photons widening. The image dims and reddens. The apparent motion crawls. None of this implies that the source slows in its own experience. Locally, physics remains ordinary. The object falls, emits, and crosses in finite proper time. The last light it sends simply cannot reach the outside because all outward paths have turned inward. These differences in perspective are not storytelling flourishes. They follow directly from relativity. Time and space are not absolute backdrops, and gravity is not a force laid on top of them. Gravity is the geometry itself. Change the geometry, and you change what straight line, simultaneous, and outward mean. The event horizon is where this redefinition becomes absolute for outward, light-like paths. Rotation complicates the dance of light further. A spinning black hole drags space-time around with it, a phenomenon called frame dragging. Paths that go with the spin can thread closer to the horizon than paths that go against it. In the ergosphere outside the horizon, but inside, a critical boundary, space-time swirl is so strong that you cannot remain at rest with respect to far-off stars. You are carried along. Light experiences this asymmetry too. Photons co-rotating with the spin can skirt nearer before being captured. Counter-rotating ones are turned away sooner. This difference leaves an imprint on the silhouette a distant observer would reconstruct. Even if the glowing background is symmetric, the shadow can appear slightly shifted or squashed, depending on the spin and the viewing angle. This asymmetry affects the shape of the shadow we would see if we look directly at the black hole silhouette against a glowing background. The first image from the Event Horizon Telescope of M 87 times shows these effects in practice. The ring is not perfectly even. Parts of it are brighter, shaped by both the direction of rotation and the way gas in the accretion disk is distributed and moving. Light bending this close to a black hole is more than a visual curiosity. It is one of the main tools we have to find and study these objects. When a black hole drifts in front of a background star, its gravity can act like a lens, focusing the starlight toward us. The star brightens for a time and then fades back, an effect called gravitational microlensing. With careful monitoring of the light curve, the way the brightness changes with time, astronomers can estimate the mass of the unseen lens. If the mass is too large for a planet or a normal star, and there is no light from the lensing object, the simplest explanation is an isolated black hole. Microlensing lets us detect quiet black holes that are not feeding and would otherwise remain hidden. Light from accretion disks gives a second window. Gas near the black hole moves at high fractions of the speed of light. Its motion produces Doppler shifts, while the deep gravitational well adds gravitational redshift. Together, these effects broaden and distort the spectrum. The detailed shape of that spectrum carries information about how fast the disk rotates, how close the inner edge sits to the horizon, and how strongly gravity curves space-time there. In that sense, a disk spectrum works like a fingerprint of conditions just outside the point of no return. The influence of a black hole on light stretches far beyond the horizon. Photons that pass at larger distances are still bent. The result can be multiple images, arcs, or rings of a background source. Sometimes the magnification is strong enough to make a very distant galaxy visible when it would have been too faint. In this way, black holes can both block light from their own interiors and help reveal the distant universe. This relationship between light and gravity is set by geometry, not by a contest of speed. Locally, light always moves at the same speed. What changes near a black hole is the shape of space-time, which reshapes the set of possible paths. Some paths curve into circles or spirals at the photon sphere. Closer in, all future paths point inward. Darkness, in the end, is not lack of light, but lack of outward routes for light to take. Once past the horizon, those routes do not exist. Everything we observe about black holes comes from outside the horizon. The glow of the disk, the structure of jets, the lensed ring and shadow. Tracking how light bends, redshifts, and fades lets us test general relativity in its strongest fields. So far, the theory's predictions have matched what we see remarkably well, but our instruments are only beginning to reach the needed precision. Following light toward the boundary naturally brings us to the horizon itself. The horizon plays a central role even though it cannot be seen directly. It is the place where every possible outward light path turns inward. Many people imagine it as a perfect sphere, like the skin of an invisible bubble around the black hole. That picture is a good start for non-rotating cases, but the exact shape depends on mass and spin, and in principle, on charge. In practice, astrophysical black holes should be nearly neutral because any charge would be quickly balanced by surrounding plasma. The simplest benchmark is the Schwarzschild black hole. In this idealized, non-rotating solution found by Carl Schwarzschild, the event horizon is a perfect sphere at the Schwarzschild radius, a distance set only by the mass. The space-time outside is spherically symmetric. No direction is special. No bulging or flattening appears. This clean symmetry is why the Schwarzschild case is the usual baseline for learning the anatomy. Real black holes almost always spin. Collapsing stars carry angular momentum. So do merging compact objects. With spin, the solution becomes the Kerr metric. The horizon is still a closed surface, but rotation drags space-time around frame, dragging, and the symmetry is no longer perfect. The horizon becomes slightly flattened at the poles and bulged at the equator, with the distortion growing as spin increases. In the extreme limit of rapid rotation, the polar radius shrinks compared to the equatorial radius, and the horizon sits closer to the center than in the non-rotating case. Spin also allows stable orbits to exist closer in, changing the inner edge of accretion disks and the detailed pattern of emitted light. Just outside the Kerr horizon lies the ergosphere, where frame dragging is so strong that nothing can stand still relative to distant stars. The boundary of the ergosphere touches the horizon at the poles and bulges outward at the equator. The ergosphere matters because it opens channels for energy extraction from the black hole's rotation. In the Penrose process, a particle entering the ergosphere can split. One piece falls in with negative energy, as measured at infinity, while the other escapes with extra energy, borrowed from the spin. A related, more astrophysically efficient mechanism, Blandford-Znajek, uses magnetic fields that link the disk and the spinning black hole to power relativistic jets. Charge modifies the geometry in calculable ways as well. The Reissner-Nordstrom solution describes a non-rotating charged black hole. The Kerr-Newman solution describes a rotating, charged one. In these metrics, the horizon position shifts, and for some parameters, two horizons appear, outer and inner. But large net charge is unlikely in nature because surrounding plasma neutralizes it quickly. Still, these solutions show how the equations respond to new parameters and help test ideas about horizons and stability. It is important to keep in mind that the event horizon is not a material shell. It is a causal boundary, defined by null paths, the routes light could take. Cross it, and you do not touch anything. You simply enter a region where all future paths, even those aimed outward, lead inward. There is no mark on the interior side that tells you where the crossing happened. The shape of the horizon lives in the geometry, not in matter. Even so, the horizon's geometry has practical consequences. In a spinning system, the bulged equator and the ergosphere affect how disks form and how jets are launched. Magnetic fields anchored in the disk and threading the ergosphere can tap rotational energy and drive powerful outflows, shaping the surroundings on scales far larger than the horizon itself. The geometry determines where energy can flow, where orbits are stable, and how close matter can circle before plunging in. Observationally, we infer the horizon through its shadow. The shadow is the dark depression in a bright background made by photon trajectories that are captured or loop many times near the photon sphere before escaping. Because the photon sphere lies outside the horizon, the shadow is larger than the horizon itself. Its apparent shape depends on spin and viewing angle. For a non-rotating case seen face-on, the shadow is a perfect circle. For a rotating case, it can look slightly compressed on one side. The EHT image of M 87 times shows a very round shadow from our vantage point, consistent with significant but not extreme spin or a viewing angle that makes the asymmetry small. In general relativity, the exterior of a settled black hole is simple, thanks to the no-hair idea. Mass and spin and charge, if present, fully determine the geometry. Two black holes with the same mass and spin are indistinguishable from the outside, regardless of how they formed. That simplicity is striking when set against the messy processes that create and feed black holes. The horizon, then, does not encode the detailed stories of infalling matter. It reflects only the few parameters that define the solution. The horizon's area adds another surprising layer. To a distant observer, a quiet black hole has a steady horizon. When mass falls in, the horizon grows. Hawking's area theorem states that, classically, the total area of event horizons cannot decrease. When two black holes merge, the area of the final horizon exceeds the sum of the two initial areas. This rule hints at a deep link between geometry and thermodynamics. Jacob Bekenstein proposed that a black hole's entropy is proportional to its horizon area. Hawking later showed that quantum effects make black holes emit radiation with a temperature inversely proportional to their mass. Over unimaginable times, an isolated black hole would slowly lose mass by Hawking radiation and shrink. But for astrophysical black holes today, accretion and mergers dominate over that slow loss. Tying area to entropy suggests that the size and shape of the horizon carry information not about the detailed contents, but about the energy and the number of internal microstates in some yet-to-be-complete theory of quantum gravity. That perspective turns the horizon from a mere boundary into a thermodynamic surface, with laws that mirror the familiar laws of thermodynamics. Our ability to test these ideas has grown quickly. The size of the M87 times shadow matches predictions for a black hole of its measured mass. Stellar orbits around Sagittarius A times give a precise gravitational potential consistent with a compact object described by general relativity. Gravitational wave signals from black hole mergers encode the masses and spins of the participants and the ringing of the final horizon. So far, in every extreme environment we can measure, the shapes and behaviors predicted by general relativity hold up. That agreement is a strong vote of confidence and also a challenge. It confirms our best gravity theory where it is hardest to test, yet it leaves little hint of where the next breakthrough will come from. In science, even a very close match between calculation and measurement can serve as a reason to examine the details more carefully, an invitation to look closer. Tiny mismatches in a shadow's outline, slight offsets in the timing of a merger's ringdown, or faint asymmetries in lensing arcs are worth watching because they might be the first hints that space-time does something new near a horizon. The shape is a test bench. The closer we get to the edge, the more the familiar rules are stressed, and the more a small discrepancy can matter. That edge also forces us to ask what it surrounds. The horizon is a boundary set by light-like paths. The singularity is the place those paths end in classical relativity. The trip from one to the other is written into the geometry. Gravity shapes both the route and the rate. Tidal forces show why. Gravity weakens with distance, so an object near a black hole feels a stronger pull on the side, closer to the center. Far from any compact object, the difference is tiny. Near a black hole, it can be huge. Stretching along the direction of fall and squeezing sideways is the natural result. Spaghettification is a light word for a hard reality. Near small black holes, the gradient is so steep at the horizon that ordinary matter is torn apart before it can notice the crossing. Near supermassive black holes, the gradient at the horizon can be mild. The same fate comes later, deeper inside. The principle is the same in both cases. Tidal forces are differences in acceleration. Ocean tides on Earth are the gentle version. Near a horizon, the same math scales up until it controls the outcome. We see evidence of this process in the sky. A star that wanders too close to a central black hole can be tidally disrupted. Its gas stretches into a stream, wraps around, collides with itself, and forms a temporary disk. That disk glows in ultraviolet and X-rays, and sometimes invisible light. The flare grows and fades in a pattern that encodes the black hole's mass and, in some cases, hints at its spin. A few events even produce jets powered by magnetic fields threading the newborn disk, with material racing out at near light speed. On smaller scales, asteroids, comets, and clouds meet the same rules. Stretch along the path, squeeze across it, heat, and radiate before the light is cut off at the boundary. From the falling traveler's point of view, nothing outside can rescue them once tidal forces dominate. The strong field geometry funnels nearby paths together. In the language of relativity, geodesics diverge in the radial direction and converge tangentially with increasing strength as the center is approached. After crossing the horizon of a non-rotating black hole, the proper time to the singularity is finite. There is no way to lengthen it beyond a certain bound. For supermassive holes, that time can be minutes or hours. For stellar mass holes, it can be milliseconds. The details depend on mass and on how much thrust is used before the crossing. But the trend is fixed by the geometry. The idea that this journey ends at a singularity is a statement about classical relativity. A singularity is where curvature grows without bound and the equations that guide everything else stop giving answers. Many physicists think this infinite signal is the theory's way of saying it is being pushed past its valid range. Quantum physics, which controls matter at the smallest scales, should matter most where densities and curvatures are extreme. That is why research points to quantum gravity, a framework that blends general relativity with quantum mechanics as the missing piece. Until we have it, the singularity is a placeholder, a region where our best map says, beyond current knowledge. Penrose's singularity theorems made the classical picture hard to ignore. He showed that with reasonable assumptions about matter and causality, trapped surfaces lead to geodesic incompleteness, a technical way of saying that classical paths cannot be extended indefinitely and must end. He also proposed cosmic censorship, the idea that singularities formed by collapse are always hidden behind horizons, so distant observers never see naked singularities. Whether censorship is always true remains an open question in some exotic scenarios, but astrophysical black holes appear to obey it. In rotating solutions, the interior adds features like inner horizons, where predictability breaks down and mass inflation can occur, suggesting that classical interiors are unstable in ways that again point toward new physics at high curvature. A second thread meets the first at the horizon: thermodynamics. Jacob Bekenstein argued that a black hole should have an entropy proportional to the area of its horizon. Entropy measures how many microscopic configurations give the same macroscopic state. The area looked like the natural quantity to track because Hawking's area theorem showed that, classically, horizon area never decreases. Stephen Hawking then used quantum field theory in curved spacetime to show that black holes radiate with a temperature inversely proportional to their mass. This Hawking radiation means an isolated black hole can very slowly lose mass and shrink. For stellar and supermassive black holes, the temperature is so low that the effect is negligible on cosmic timescales. Accretion and mergers easily dominate, but the concept creates a deep puzzle. The puzzle is information. If a black hole forms from matter in a pure quantum state and then evaporates by emitting thermal radiation that seems to carry no information, where did the information go? Quantum mechanics says information is conserved. General relativity by itself seems to allow loss. This is the information paradox. Many ideas aim to resolve it. Black hole complementarity suggests that no single observer ever sees a violation. For an outside observer, information is stored and slowly re-emitted from a stretched horizon, while for an infalling observer, nothing special happens at the boundary. The two stories cannot be compared directly, because no observer can access both descriptions. The firewall argument challenges this picture, claiming that unitarity in the equivalence principle cannot both hold in a simple way and that consistency might require a high-energy firewall at the horizon. Other views look to quantum hair, subtle charges or soft excitations that store information on or near the horizon, or to islands in modern calculations that reproduce the expected page curve, showing that the entropy of Hawking radiation rises and then falls as if information returns in correlations later in the evaporation. String theory offers the fuzzball proposal, where what we call a black hole is actually a horizonless, stringy object whose many microstates mimic the exterior geometry while replacing the interior with a complex structure that stores information. Loop quantum gravity suggests that quantum geometry can eliminate the singularity and replace it with a bounce or a high-density core with finite curvature. Holography, especially the ADS, CFT correspondence, gives a powerful toy model in which gravity in a volume is equivalent to a quantum theory on its boundary. In that setting, unitary evolution on the boundary strongly suggests that bulk black holes do not destroy information, even if the detailed mechanism is hard to extract for our universe. Each approach matches part of the picture and leaves other parts open. Observations give us handles on the outside story, where the theory is clearest. The ring down after a merger, the fading gravitational wave tone of the final black hole should carry overtones that depend only on the mass and spin of the remnant in general relativity. Measuring these tones checks the no-hair idea. So far, the signals fit the predictions within current uncertainties. Searches continue for echoes, late-time wiggles that some alternatives to horizons might produce if the interior replaced the classical boundary with a reflective layer. Nothing has been confirmed, but the methods are improving. On the imaging side, very long baseline interferometry maps the shadow scale and its asymmetry to test the space-time metric near the horizon. On the electromagnetic side, high-resolution X-ray spectra probe the innermost stable orbits and measure spin by how close the disk can sit. On the dynamical side, precise tracking of stars near Sagittarius A times checks for tiny precessions predicted by relativity. Small deviations matter because they could point to alternatives. Compact objects without horizons, boson stars, gravastars, wormholes can mimic some signatures while changing others. Many would produce slight changes in ringdowns or different shadow edges. They could also alter how matter piles up at what would otherwise be a one-way boundary. So far, black holes as described by general relativity remain the simplest way to match the full set of data. But the door stays open because pushing on that door is how we learn where the next theory must start. Spin complicates the interior and the exterior at once. Frame dragging twists the paths of light and matter, shifting the inner edge of disks and changing the efficiency with which infalling gas can radiate before crossing the line. The innermost stable circular orbit moves inward for prograde orbits, making disks hotter and spectra harder. Spin also powers energy extraction. Magnetic fields that thread the ergosphere can draw on rotational energy, launching jets that carry power far beyond the galaxy. This link between the smallest scale, the horizon, and the largest scale, the galaxy's gas, means black holes help regulate star formation. Heat and momentum from jets can keep gas hot and prevent it from collapsing into new stars, a feedback loop that helps set the growth of galaxies. Charge is expected to be small in nature because inflowing plasma neutralizes it. Still, charged solutions teach us how horizons and inner structures move when new parameters enter. They also highlight the role of inner horizons and their instabilities, again pointing toward quantum effects as regulators of extreme behavior. Even if large net charge is rare, understanding the equations with charge improves our intuition for how gravity and electromagnetism share the stage in strong fields. From the viewpoint of a traveler, the final approach to the classical center erases familiar scales. After the horizon, space and time swap roles in a meaningful way. The radial coordinate behaves like time, and moving inward becomes as compulsory as moving forward in ordinary life. Attempts to hover or turn back translate into choices about how to spend remaining proper time rather than ways to avoid the end. For a non-rotating hole, every time-like path terminates at the central point. For a rotating hole, paths meet a ring singularity in the classical model. But instabilities near inner horizons make the realistic interior more complicated and likely to differ from the neat textbook diagram. In both, the message is that classical geometry forces a finish, while quantum geometry may redraw the final step. Back outside, the horizon's area behaving like entropy connects black holes to ordinary thermodynamics. There are laws of black hole mechanics that mirror the four laws of thermodynamics. Surface gravity plays the role of temperature, horizon area plays the role of entropy, and mass and spin map to energy and work terms. Hawking's radiation gives these analogies physical backing. Over incredible times, an isolated black hole would evaporate, with its temperature rising as it shrinks, and the final stage is dominated by quantum processes beyond our current reach. For supermassive black holes in galactic centers, the environment and timescales keep evaporation irrelevant. Accretion and mergers grow them faster than they could lose mass. The page time, the moment when half of the black hole's entropy has been radiated, if evaporation ran alone, marks a turning point in many information arguments. In models that include islands, the entropy of the radiation rises at first and then falls, consistent with unitary evolution. These results come from simplified spacetimes, but fit naturally with the holographic view that information is not lost. Translating these insights to the astrophysical case, where a black hole sits in a complex environment, remains an active effort. The broad lesson holds. Entropy, area, and information are tied together at the boundary. Even without a complete quantum theory, we can compute many strong field effects precisely. The gravitational redshift of lines from iron in the inner disk, the broad profiles that combine Doppler and relativistic beaming, and the timing of hotspots orbiting close to the last stable orbit all encode the metric. Polarization of X-rays, now measurable, traces magnetic geometry and the way light scatters in strong gravity. The more channels we measure timing, spectrum, polarization, image, the tighter the tests become. Any consistent departure could show us how to modify the equations at the edge of their range. The structure we have built, photon sphere, horizon, ergosphere, jets, disks, rests on a single idea. Gravity is geometry. That idea passes everyday tests, like GPS timing and Mercury's precession, and it passes hard tests near horizons. Where it signals trouble is exactly where we expect quantum rules to take over. That is why the horizon is so valuable. It is a natural laboratory that focuses both the success and the limits of our best theory. Watching light bend and fade, listening to space-time ring after a merger, mapping how area grows in a collision, all of these are ways of reading the geometry at its sharpest point. The singularity sits beyond what we can probe with light, but the approach to it leaves fingerprints we can see. Tidal disruptions trace the gradient of gravity. Shadow sizes trace the photon sphere. Ring-down tones trace the bare parameters of the solution. Jets trace the link between spin and magnetic fields. Feedback on galaxies traces the far reach of energy released just outside the boundary. Each clue touches a different part of the same structure, and together they tell a coherent story that leaves a small, deliberate gap in the center where future physics belongs. Einstein's unease about singularities was not a mistake so much as a sign that the picture could not be the final word. He trusted geometry, but also sought completeness. And a point of infinite density is not a complete answer. The decades after him showed that horizons are real and singularities are generic in classical gravity. The decades ahead aim at the missing layer, a quantum description that keeps the successes of the exterior while replacing the interior pathologies with something finite and lawful. The first steps of that description already tie area to entropy, connect evaporation to information, and link boundary data to bulk dynamics in holographic models. What they will say about the exact fate of matter and the exact structure inside the boundary remains open. The only clear demand is that the final account must reduce to general relativity where it works and to quantum mechanics where it rules, and it must do both at once near the edge where every outward path vanishes. There is a precise distance around a black hole that separates two very different outcomes. Outside it, escape is possible in principle. Inside it, every path carries you inward. There is no surface to mark it, no grit, no film, nothing to brush against. If you were falling, your eyes would not pick out a line, yet its location is exact, fixed by the equations that describe space-time. This is the event horizon, a silent border between where signals can still get out and where they cannot. We call it a horizon because, like the line that meets sea and sky, it marks the limit of what can reach us. Unlike Earth's horizon, it does not retreat as you move. It stays where it is relative to the black hole, and once you are across, no message can return. The speed of light remains the top speed, and inside this boundary, even light's best effort points inward. A helpful picture is a river flowing toward a waterfall, far from the drop. The current is quick, but you can still swim away. Near the edge, the flow matches your best possible stroke. Past the lip, the river carries you faster than any attempt to push back. In the same way, you are not being pulled by a rope. Rather, space itself is flowing inward faster than light can move outward. Beyond the horizon, a way no longer leads outside. If you watch an object fall from a safe distance, the scene grows peculiar. Each photon it sends must climb from a deeper well. Climbing costs energy, so the light stretches to longer wavelengths, gravitational redshift. The object appears to slow, then crawl, and never quite reach the horizon. Its signal fades as the color slips beyond your detectors. That is not the experience of the falling traveler. In their own frame, the crossing is uneventful. No thud, no flash, no sharp border. What changes is the view outward. The outside sky warps, light bends around, and because the traveler moves toward that incoming light, many directions look blue shifted. The disagreement between these views is not a mistake. It is relativity at work. The horizon is a feature of space-time, not a thing in space, and crossing it depends on who measures and how. For spinning black holes, another surface appears outside the horizon, the static limit. Between that limit and the horizon is the ergosphere, where space-time is dragged around by the black hole's rotation so strongly that standing still relative to the distant stars is impossible. Inside this zone, you can still escape if you move the right way, but you cannot hover. Even beams of light are carried along by the swirl, an effect called frame dragging. A horizon does not keep the same size if the black hole's mass changes. When a black hole swallows gas, stars, or another black hole, the event horizon expands. The surface moves to a new position in space-time. In principle, the reverse can happen extremely slowly through Hawking radiation, a quantum effect that lets black holes radiate and lose mass. But for astrophysical holes, this shrinkage is negligible compared with the age of the universe. An unexpected link ties the horizon to thermodynamics. In the early 1970 seconds, Jacob Bekenstein proposed that a black hole carries an entropy proportional to its horizon area. That idea suggested the horizon encodes information about what has fallen in, at least in a coarse way. Stephen Hawking extended the story by showing that quantum fields in curved space-time make black holes radiate with a temperature that depends on mass. Large black holes are cold. Their temperature is far below the cosmic background glow. In this framework, a simple geometric quantity, the area behaves like entropy, and the horizon acts as a thermodynamic surface. Hawking also proved an area theorem in classical relativity. The total area of event horizons cannot decrease. When two black holes merge, the final horizon's area exceeds the sum of the originals. This mirrors the second law of thermodynamics and ties the arrow of time to geometry. Still, the horizon remains intangible. We do not see it directly or park a probe on its edge. We infer it from what happens just outside. The EHT image of M87 times shows a dark shadow bounded by a bright, lensed ring. That shadow is set by the photon sphere, which lies outside the horizon, but its scale and shape reflect the underlying space-time. The boundary itself stays unseen, even as it sculpts all we can measure. Some proposals suggest the horizon might not be as featureless as the simplest picture says. Firewalls, hypothetical bands of high-energy quanta at the boundary, have been offered to address the information paradox. Other ideas allow information to seep out subtly, altering the late-time radiation. None of these have observational support so far, yet they mark the horizon as an active frontier where quantum theory and gravity meet. For us, the horizon is also a conceptual line. It marks what we can know from outside. Every black hole measurement, disk light, jets, shadows, stellar motions comes from the region just beyond it. The interior is hidden not by poor instruments but by cause and effect. Signals cannot cross outward. Past that invisible surface, space-time's roles shift. All forward paths end at the singularity, and familiar rules may give way to ones we have not yet written. Time near a black hole does not behave the way our daily clocks suggest. The difference is not that clocks break, but that gravity reshapes the relationship between observers. Near the horizon, that reshaping reaches an extreme. Far away, you would judge a falling clock to run slow, ever slower, as it nears the boundary. For the falling observer, time passes normally while the outside universe appears to speed up. This is a direct outcome of general relativity. In empty, flat space-time, everyone can agree on a second. Curvature changes that agreement. The deeper you sit in a gravitational well, the slower your clock runs relative to one higher up. We live with a tiny version of this. GPS satellites tick slightly faster than ground clocks because they orbit farther from Earth's center. Engineers correct for this difference. Near a black hole, the effect dominates what we see. If you fell toward the horizon, your seconds would feel ordinary. A distant observer would watch your clock slow as you approached, then appear to stop. Your light would arrive at longer and longer intervals, stretched to lower energies until it disappeared. That is not an illusion. It is a real difference in elapsed time between two frames. You would cross in finite proper time and continue inward. The distant observer would never receive the crossing signal. The opposite view is just as odd. As you fall, light from the outside world reaches you along more curved paths. Because you are moving inward, much of that light is blue-shifted, boosted in energy. At the same time, sequences of outside events appear to speed up. A far-off clock might seem to race. Large-scale changes, stellar motions, even slow galactic evolution would be compressed. In simple thought experiments, if you could somehow survive long enough on the way down, you could witness an accelerated version of distant futures. In reality, tidal forces and extreme conditions end the trip before that thought experiment plays out for any human observer. But the trend follows directly from the geometry. This relativity of when is one of the challenges in reasoning about black holes. An event that occurs after you cross the horizon might be never for an outside observer, because no signal from it can escape. There is no single shared timeline that covers both viewpoints once the horizon divides them. That is not a flaw. It is what relativity predicts when gravity is strong. The geometry behind these statements can be made precise. In the Schwarzschild solution, the coordinate used as time by a distant observer becomes ill-suited near the horizon. Inside, the radial coordinate takes on the role that time plays outside. It must decrease. Moving toward the center is as compulsory as stepping into tomorrow. There is no choice to hold radius constant any more than you can hold time still. In the Kerr solution for rotating holes, the picture becomes richer. Frame dragging twists space-time, so time is not aligned the same way everywhere. The horizon still marks the no-escape limit, but the experience of time depends on distance and on motion relative to the spin. In the ergosphere, standing still relative to the distant stars is impossible. The fabric itself is carried around. These time effects show up in measurements. Gas in an accretion disk orbits close to the horizon at a large fraction of light speed. Its light is Doppler shifted by motion and red shifted by gravity. By modeling these line shapes and continua, astronomers locate the inner edge of the disk and infer spin, which in turn encodes how space-time is shaped near the horizon. Time dilation also colors the way we think about Hawking radiation. To a distant observer, evaporation is glacial, far slower than the age of the universe for stellar or supermassive black holes. For an observer falling in late in that process, outside changes could appear compressed, though no real traveler could witness both stories and compare notes. Timing matters for the information paradox as well. If information escapes in correlations within the outgoing radiation, the when and how of that release becomes central. Time near the horizon refuses to be simple, complicating any naive bookkeeping of bits. Even so, the core lesson is steady. Time near a black hole depends on where you are and how you move. The closer you are to the boundary, the more your experience splits from that of the wider universe. That split is not a footnote, it shapes how black holes look to us and sets the limits of what outside observers can ever learn. The singularity's secrecy is not only a matter of distance or darkness, it is enforced by a barrier in the structure of time itself, sealing events inside so they never rejoin the timelines traced by those who remain outside. Hawking's result does more than add a small detail to the picture. It connects gravity, quantum theory, and thermodynamics in a single place. The radiation has a nearly thermal spectrum, like the glow from a warm object, but the temperature is set by gravity. The heavier the black hole, the lower the temperature. The lighter the black hole, the higher the temperature, because the temperature is tiny for any large mass. Normal astrophysical black holes are, for all practical purposes, cold and dark in this sense. There is a simple way to think about the energy accounting without leaning too hard on the particle pair story. Quantum fields near the horizon do not behave exactly as they do in flat space. The curved geometry changes what vacuum means for different observers. To someone far away, the state that looks like empty space near the horizon contains a trickle of outgoing quanta. Energy conservation then says that the black hole must lose mass to pay for that trickle. Whether you picture it as separated particle pairs or as a change in the field's ground state, the outside prediction is the same: a slow outward flow and a slow loss of mass. The rate of evaporation depends very steeply on mass. A black hole with the mass of the Sun would take a time far larger than any current cosmic age to evaporate. Increase the mass to millions or billions of suns, and the evaporation time becomes so long that it is not meaningful for the history of galaxies. Decrease the mass a lot, and the process speeds up. Hypothetical small black holes formed in the early universe, if they exist, would be the only ones whose Hawking glow could matter today. Astronomers search for their signals in high-energy light and in particle detectors, but no convincing detection has been made. As a black hole slowly loses mass, its horizon shrinks. The temperature rises because temperature and mass move in opposite directions here. Near the end, if nothing interrupts the process, the radiation becomes intense, and the final stage is brief. The output would include many kinds of particles allowed by physics at those energies. For a black hole that started small enough, the final moments could be detectable as a burst of high-energy photons. For the large black holes we see in galaxies, that end lies so far in the future that it does not affect any present-day observation. Hawking radiation brings the area-entropy link into sharp focus. Earlier, we used area to reason about entropy in a classical sense. With radiation, a true temperature appears, and the laws of black hole mechanics take on the form of the laws of thermodynamics. Surface gravity behaves like temperature. Horizon area behaves like entropy. Mass and spin play the role of energy and work. When two black holes merge, the final horizon area grows, and the entropy grows with it, while the lost orbital energy flows away in gravitational waves. The parallels are tight enough that many physicists see them as more than analogy. They look like real thermodynamics for gravity. If black holes radiate and shrink, a question follows: where does the information go? If the outgoing radiation is purely thermal, it carries no record of the specific state of the matter that fell in. Quantum mechanics, however, says that information is not destroyed in closed systems. This tension is the information paradox. Several ideas try to resolve it without breaking quantum rules. One is that very subtle correlations in the outgoing radiation, too fine to see in simple calculations, carry the information back out over long times. Another is that the horizon is not completely featureless when quantum effects are included, and that these small structures, sometimes called soft hair, encode the needed data. Some arguments point to a division of stories. For an outside observer, information never truly passes beyond a stretched quantum layer near the horizon. For an infalling observer, physics looks smooth at the crossing. Other proposals argue that these two stories cannot both hold and suggest a firewall, a violent zone at the horizon, though that picture clashes with the idea that nothing special happens at the boundary for the infaller. Newer calculations, using islands in simplified models, reproduce the expected rise and fall of radiation entropy, hinting that unitarity can be saved. The details are active research, but the outline is steady. The horizon is where gravity and quantum physics must be joined. The evaporation picture also raises practical questions. If a black hole is in a real astrophysical setting, it is rarely isolated. Gas drifts in, stars pass nearby, and black holes sometimes merge. Any mass gained this way overwhelms the tiny mass lost by radiation. A black hole at a galaxy's center can grow for billions of years, even while its Hawking temperature stays almost at zero. The generalized second law accounts for this. The increase in horizon area from accretion ensures that the total of black hole entropy plus ordinary entropy outside does not go down. In that sense, feeding a black hole is like adding a huge number of microscopic states to the system in one step. Observationally, we test the framework from the outside. We measure how close disks can orbit before plunging. We use X-ray spectra to read gravitational redshift and Doppler beaming near the last stable orbits. We map the size of shadows against mass estimates. We time the ringing tones after mergers and compare them with the modes predicted by general relativity. Each of these checks the geometry that sets the horizon's position and the photon sphere's scale. None of them see Hawking radiation directly for large holes, but all of them test the arena in which quantum gravity will have to fit. Primordial black holes, if they formed from early density spikes, would populate a wide range of masses. The smallest would have evaporated by now. Slightly larger ones could still be evaporating today, giving off gamma rays. Searchers look for isotropic backgrounds and for flashes. Strong limits exist at many masses, from lensing surveys, cosmic microwave background measurements, and dynamical effects on stars and gas. A narrow window remains in some ranges. Whether primordial black holes make up any part of dark matter is still under study, but current data push them to be at most a small fraction over most masses. This keeps the focus on stellar mass and supermassive black holes for most of what we observe. The freezing, seen by a distant observer, and the smooth crossing seen by an infaller lead to another question. Does anything ever actually reach the horizon in the outside description? The answer is yes, when you think in terms of what distant clocks measure for events at finite distance. The light from the final crossing cannot reach the outside, but the matter itself becomes part of the black hole's mass and angular momentum in the external fields. Its effects on the metric appear in finite time for observers far away. In practice, we see this in how quickly the orbits of nearby bodies adjust and in how the ring down after a merger settles to the parameters of the final black hole. The fields outside do not wait for an infinite time to change. They reflect the new configuration once the matter is close enough that no more outward influence is possible. Close to the horizon, classical pictures tell us that nothing special happens locally for a large black hole. Quantum pictures warn us that the vacuum state depends on where you are and how you move. An observer who hovers very near the horizon must fire rockets to hold station. In that accelerated frame, the vacuum looks like a bath of particles with a temperature, the Unruh effect. The closer you hover, the higher the temperature you measure. This is not Hawking radiation in the strict sense, but it helps build intuition for why observers disagree about what the vacuum contains near strong gravity. An infaller, in free fall, does not see that same bath at the crossing in the classical theory. Rotation alters almost every detail near the edge. Prograde orbits can sit closer to the horizon than retrograde ones. The efficiency with which an accretion disk converts gravitational energy to radiation increases with spin because material can fall from deeper in the potential well. The inner disk's brightness and spectra carry that signature. The ergosphere allows energy extraction through processes that tap rotational energy, either with particles, Penrose process, or, more plausibly in astrophysical settings, with magnetic fields, Blandford-Znajek. In both cases, the power comes from spin and flows outward before crossing the boundary. The horizon remains a one-way surface throughout. Magnetic fields and plasma behavior add complexity that pure geometry alone does not capture. The disk is not a smooth, quiet ring. It is turbulent. Instabilities drive angular momentum outward and mass inward. Hotspots orbit and shear. Flares rise and fall. Polarization measurements of X-rays and sub-millimeter light trace the structure of fields and the way light scatters near the edge. These details let us build models of how matter behaves where gravity is strongest and test the metric with fresh kinds of data. The life story of a typical stellar mass black hole is simple in broad strokes. It forms from the core collapse of a massive star or from the merger of two compact objects. It accretes sporadically if it has a companion star, brightening in X-rays when gas feeds the disk. It may merge with another black hole, producing a gravitational wave signal and a larger remnant with a bigger horizon. Over time, in an empty universe, it would eventually evaporate, but that stage lies beyond any time we can now probe. For a supermassive black hole, the story is similar, but on a larger canvas: growth by accretion when gas is plentiful, quiet phases when fuel is scarce, and occasional large mergers that reshape both the black hole and the host galaxy's center. The role of the horizon in all these chapters is steady. It is the boundary that sets what can leave and what must stay. It sets the stage for the last stable orbits of matter and for the photon trajectories that draw the shadow. It joins gravity with thermodynamics by giving area the meaning of entropy. It anchors open problems in quantum theory by forcing a sharp question about information. None of these roles depend on a dramatic physical surface. They depend on the causal structure defined by the geometry. On the human scale, the numbers are far outside our daily sense. Time slows by a tiny, measurable amount between a mountaintop and sea level, near a horizon. The same principle stretches to extremes. Light bends by a minuscule angle near the sun. Near a horizon, it can circle in loops. Escape velocity on Earth is fast, but reachable. At the horizon, the needed speed equals light speed. The same rules extend smoothly from the mild to the extreme. That continuity is what makes black holes useful for testing theories. If the rules ever fail, they are most likely to fail where the curvature is highest and the equations are stressed. That is why people study tiny deviations in shadow shapes, slight delays in ring down tones, and subtle shifts in how light curves around the edge. Hawking's calculation places a clock on every isolated black hole, even if the tick is far too slow to hear. In a young universe full of gas and stars, that clock is irrelevant. In a very old universe with little left to eat, the clock controls the last act. The radiation cools the environment while the black hole heats as it shrinks, the opposite of how ordinary objects behave. The end comes quickly once the mass is low enough. What exactly happens in the final instant depends on physics at energies we do not yet access in experiments. The broad picture is still a steady fade followed by a brief, bright finish. Between the outside view and the inside view lies a clean dividing line drawn by the speed of light. and by geometry. Signals cannot cross outward once the line is passed. From outside, we infer properties by watching what happens just short of that line. From inside, motion toward the center becomes as compulsory as the passage of time. The two stories do not merge into one, because no single observer can live both at once. That divide is not a failure of description. It is the structure of space-time around a horizon. The energy released before the crossing can change whole galaxies. Jets heat, gas, and slow the birth of stars. Outflows stir halos and carry heavy elements far from their sources. Feedback on these scales shows that a boundary only a few light hours or light days across can influence regions millions of light years wide. The chain of cores runs from magnetic fields and orbits near the horizon to gas cooling and star formation far away. In that way, the most compact objects help set the pace of cosmic structure. Hawking radiation adds a final thread to that chain by setting a natural fate for isolated black holes. Nothing in daily experience gives a direct feel for a cold object that grows hotter as it shrinks. Nothing in daily experience prepares us for a surface that is not a surface yet follows the rules of temperature and entropy. The equations do the work of tying these ideas together. The measurements we can make light curves, spectra, polarization, images, and gravitational waves keep confirming the parts we can reach. What remains out of reach sits behind the same boundary that sets the rules for what we can see. Supermassive black holes at galaxy centers do not run their hosts like engines, but their reach extends far beyond the tiny region near the event horizon. When gas drifts inward, gravity compresses and heats it. If enough gas reaches the inner parsec, accretion turns on and the nucleus brightens. We call this an active galactic nucleus. During active phases, the core can outshine the whole galaxy. When fuel is scarce, the same black hole goes quiet and leaves only faint radio or X-ray traces. This on-off cycle unfolds over millions of years and is set by how galaxies move gas toward their centers. Gas rarely falls straight in. It carries angular momentum that must be moved outward. Large-scale bars in stellar disks can torque gas along elongated paths. Galaxy mergers stir orbits and push cold gas inward. Even without mergers, spiral waves, turbulence, and clumpy clouds can nudge gas toward the middle over long times. In the inner few light years, magnetic turbulence in the disk transports angular momentum outward, so mass can drift inward and heat up as it loses energy. There is a natural brightness limit. Infall releases radiation that pushes back on ionized gas. The Eddington limit marks the balance between outward radiation pressure and inward gravity. Many bright quasars shine near this limit, while lower accretion rates produce dimmer, thicker, and less efficient flows. The accretion mode matters. Thin, radiatively efficient disks at high rates, hot, puffed, radiatively inefficient flows at low rates. Spectra, timing, and polarization patterns help identify which mode we are seeing. Feedback is how a tiny core influences a giant system. Energy and momentum, from near the horizon couple to gas on kiloparsec and even megaparsec scales. In radiative quasar mode, intense light heats and pushes central gas, sometimes driving fast winds. In kinetic radio mode, jets and broad outflows carry power far out. In galaxy clusters, jets inflate bubbles in the hot X-ray gas. Those cavities rise, stir the medium, and keep it from cooling too fast. In smaller galaxies, winds can sweep out cold gas and briefly starve star formation. Fuel arrives, the core brightens, outflows heat and stir. Fueling drops, The core dims, gas cools, and the cycle starts again. Black hole mass correlates with properties of the host bulge. The mass-velocity dispersion and mass-bulge-mass relations suggest coevolution. As the bulge grows, the black hole grows, and feedback self-regulates both. The link is not a single mechanism, but a pattern seen across many systems. Near galaxy centers, stellar speeds imply a compact mass that cannot be explained by stars alone. The simplest answer is a supermassive black hole. Our own Milky Way shows this cleanly. Infrared tracking of individual stars near the center reveals tight orbits with periods of years. The enclosed mass is about 4 million suns inside a region smaller than our solar system. A dense cluster of remnants would spread out. A single compact object fits the data. Most of the time it is quiet, with brief flares when small clouds feed it. In M87, a well-collimated jet extends far beyond the galaxy. Its power and structure point to a spinning black hole tapping rotational energy through magnetic fields. Radio images resolve a bright ring on photon sphere scales, showing space-time curvature shaping the light. Growth happens by gas accretion and by mergers. Accretion can be efficient. A significant fraction of rest mass turns into radiation and heat. The quasar population across cosmic time shows that vast amounts of gas fell into black holes when the universe was young. Mergers add mass in larger steps. When galaxies collide, their central black holes spiral inward through dynamical friction, form a bound pair, and harden by slinging nearby stars and interacting with gas. Once close enough, gravitational waves carry away the remaining energy and angular momentum, and the holes coalesce. The last moments produce a burst of gravitational waves and a kick to the remnant. In massive galaxies, the kick rarely ejects the remnant. It settles back to the center, now heavier and often spinning differently. Duty cycles matter. A single galaxy does not shine as a quasar for billions of years. It turns on and off many times, each active episode lasting millions of years. The sum of many episodes builds the final mass. We read this history in the backgrounds of integrated accretion light, in present-day black hole mass functions, in spin distributions, and in how common active nuclei are at different epochs. Each black hole has a sphere of influence, where its gravity dominates over that of surrounding stars. For supermassive black holes, this can span light years. Inside that radius, stellar motions map the black hole's mass. Outside, the galaxy's mass takes over. Measuring this requires sharp imaging and detailed modeling. Many galaxies now show secure central masses, revealing that black holes are common in bulge-dominated hosts. Jets deserve special focus because they connect the smallest and largest scales. Near the hole, magnetic fields thread the inflow and the ergosphere. Rotation twists the fields and launches plasma along the spin axis. The jet accelerates and collimates near the core, then interacts with interstellar and intergalactic gas farther out. Internal shocks produce radio, optical, and X-ray emission. The jet inflates lobes larger than the host galaxy, displacing hot gas and depositing heat. In clusters, these lobes appear as X-ray cavities. The work required to inflate them can balance the cooling of the cluster core. On galactic scales, jets and winds carve channels through dense gas and regulate how quickly fuel reaches the center again. Star formation and black hole growth are linked but not synchronized. A merger can trigger a starburst that builds a bulge, while the black hole brightens later as gas sinks to the inner parsec. Or a black hole may have a brief feeding event before a longer episode of steady star formation, averaging across many cycles, yields the tight scaling relations. Locally, feedback can be harsh. Radiation pressure and shocks can disrupt clouds near the nucleus. Globally, low-level heating can keep gas from catastrophic cooling without blowing it away, maintaining a gentle balance for long periods. Not all hosts are the same. Disk-dominated galaxies with small bulges can still harbor massive black holes. Dwarf galaxies may host intermediate mass black holes between stellar and supermassive scales, though firm examples are rare. These lighter seeds could be the starting points from which giants grew. Direct collapse models propose that, under special early universe conditions, massive gas clouds formed black holes of 10 to the power of 4, 10 to the power of 6 solar masses, without first making stars. Near-Eddington accretion, repeated over many bursts, can then grow billion solar mass holes by the time the universe is less than 1 billion years old, matching high redshift quasars. The Milky Way's center functions as a nearby lab. Infrared monitoring sees hotspots orbiting near the innermost stable circular orbits, flaring and cooling on short timescales. Polarized sub-millimeter light traces magnetic structures in the inner flow. Rotation measures limit how much gas actually crosses the horizon, showing that low luminosity accretion can be inefficient at radiating away energy. Most of the heat goes in. The result is a dim nucleus, despite a massive central object. The surrounding star clusters record past activity. Young stars on eccentric disk-like orbits hint at phases when gas rings fragmented into stars before feeding the black hole. Older, randomly oriented stars trace a slower background of evolution. Occasionally, a star passes too close and is tidally disrupted. Its debris forms a temporary disk and lights up the nucleus in ultraviolet and X-rays for months to years. These tidal disruption events act as brief beacons that reveal the engine's environment. Between the inner accretion flow and the larger galaxy sit structures that help or hinder fuel, nuclear spirals, circumnuclear rings, and dusty lanes, gravity torques, turbulence, and magnetic stresses shift angular momentum. Simulations that include stars, gas, feedback, and black holes show lumpy, multi-phase inflows that vary with time, matching the irregular light curves seen in active nuclei. Within the central few hundred parsecs, winds and supernovae from young stars can either drive gas inward or clear it outward, depending on geometry and timing. Binary black holes pose a final parsec challenge in simple models. Once stars that can carry away energy are depleted, hardening can stall. Real galaxies are not perfectly round. Triaxial shapes and steady refilling of the loss cone keep stars available to interact. Gas disks can also extract angular momentum through torques and drag. Once separations are small enough, gravitational wave emission dominates and brings the pair to merger. Future space-based detectors are expected to track these in spirals, measuring masses and spins and testing relativity in the strong field regime. Mass and spin encode growth history. Long, steady, aligned, accretion tends to spin a hole up, pulling the innermost stable orbit inward and boosting radiative efficiency. Short, randomly oriented episodes keep spin moderate. Major mergers can tilt the spin axis or spin the hole down, depending on orientations and mass ratios. Observationally, broad iron Kalfa-line profiles and continuum fitting in special cases estimate spins. Jet power and collimation hint at spin through energy extraction efficiency. Patterns suggest that powerful radio cores often host high-spin holes, while many quiet nuclei may have mixed spin histories. The reach of a central black hole extends to the circumgalactic medium. Outflows can heat halo gas, reducing the rate at which fresh, cool material falls back onto the galaxy. This helps keep massive galaxies red and quiescent with old stellar populations. In less massive halos, outflows can escape and carry heavy elements into intergalactic space. Feedback thus ties together star formation histories, chemical enrichment, and the shapes of galaxy spectra across time. Even in quiet phases, the core shapes stellar structure. Some galaxies show steep central cusps, others have shallow cores. Binary black holes can scour stars from the center during mergers, leaving low-density cores. Later inflow and star formation can rebuild dense centers. Nuclear star clusters, compact star groups at the very center, sometimes coexist with black holes. Their ages, masses, and motions help trace whether stars migrated inward or formed in place from pooled gas. Very close to the black hole, the geometry sets a few decisive distances. The innermost stable circular orbit marks where stable orbits end and plunging begins. For non-rotating holes, it lies farther out. For rapidly spinning holes, it moves inward, allowing hotter, more efficient disks. Polarization, timing of orbiting hotspots, and energy shifts of spectral lines probe these scales. Together with direct imaging of shadows and rings, such measurements test whether the space-time really follows the Kerr solution or shows small departures. On cosmic scales, the balance between feeding and feedback shapes galaxy populations. Without heating from central engines, gas in big halos would cool too fast and make too many stars. With too much heating, gas never cools, and galaxies would be too faint. Models that include black hole feedback match observed galaxy numbers, colors, and masses better than those that do not, pointing to central engines as key regulators. The details remain active work. How jets deposit heat without shredding delicate structures, how radiation couples to dusty gas, and how different gas phases share energy. Low-mass galaxies test the limits of this picture. Their shallow gravity wells make them sensitive to outflows. If they host black holes, even modest accretion events could clear gas and stall star formation for long periods. Surveys find hints of active nuclei in some dwarfs, but the sensors and mass measurements are incomplete. Weighing these small black holes will test ideas about early seeds and initial growth. Across all of these cases, the event horizon sets the core rule. There is a boundary from which nothing returns, yet the energy released before crossing can change entire galaxies. That contrast microscopic boundary, macroscopic reach, makes supermassive black holes both laboratories for gravity and levers for galaxy evolution. As instruments improve longer baseline radio arrays, sharper X-ray spectrometers, time domain surveys, and space-based gravitational wave observatories, the map of scales fills in. We will measure more shadows and rings, time more stellar orbits, track more flares and tidal disruptions, and hear more mergers. The broad outline is steady. Gas must lose angular momentum to feed the center. Accretion converts mass to energy with high efficiency. That energy, carried by light, winds, and jets, couples back to gas over many scales. Over time, this sets black hole masses in step with bulge properties and guides how galaxies live. In quiet phases, the nucleus hardly glows. In active phases, it can outshine the host. In every phase, the presence of a horizon defines what the core is, while its influence is written in the light curves, spectra, polarization patterns, jets, winds, and stellar motions that we can observe outside that boundary. For generations, black holes were things we knew only through mathematics and indirect evidence. Imaging their shadows moved them into direct observation. It also created a new way to test gravity in its strongest form. With the first pictures in hand, the focus turned to adding detail, measuring polarization, tracking changes in time, and comparing what we see with computer models that evolve magnetized plasma in curved spacetime. Polarization maps are especially useful. They show how light waves line up, which in turn traces magnetic fields near the horizon. In M87*, polarization patterns outline ordered fields that can guide and collimate a jet. That agrees with models where rotation and magnetic tension help extract energy from the black hole and its inner disk. For Sagittarius A*, polarization and rapid flickering reveal a more chaotic flow, as expected for a source that accretes at a very low rate. These maps do not just draw pretty patterns, they constrain the strength and geometry of fields and the density of the plasma near the boundary. Time is the next frontier. Matter, near Sagittarius A times, moves on minute scales, so a single snapshot mixes many states. Teams now aim to build short movies by combining many nights of data and by enlarging the network. More radio stations on more continents, new receivers at shorter wavelengths, and better clock and weather corrections all sharpen the view. A denser array can separate the bright crescent from the thinner, fainter photon ring that circles the shadow. Measuring that ring's size and shape again tests the space-time metric. If it matches the Kerr solution of general relativity within small errors, the theory wins another round. If it shows a consistent offset, that would be a signal to examine new physics. Closer to home, the orbits of individual stars around the Milky Way's center give a clean probe of gravity. The star called S, 2 swings, within a few light hours of Sagittarius A*. Its spectrum reddens and then returns as it passes closest approach, a direct sign of gravitational redshift. The path of its orbit slowly rotates in the plane as well, a relativistic precession long predicted and now measured. Both effects match general relativity. They also rule out many alternate ideas, like compact clusters of dark remnants, because such clusters would not remain stable and would not reproduce the same precise timing. X-ray astronomy adds another set of tools. Gas in the inner disk around some active nuclei shows a broad ion emission line. The line's red wing is stretched by strong gravity, while the blue peak is boosted by orbital motion. Fitting these shapes estimates how close the inner edge of the disk lies to the horizon, which depends on spin. When short flashes of X-rays strike the disk, echoes return as the emission reprocesses this reverberation, maps the light travel times through the inner few light hours. Together, line, shapes, and echoes let astronomers weigh the black hole, measure spin in some systems, and check whether orbits end where the Kerr metric says they should. Tidal disruption events offer short, bright tests. When a star is torn apart, its debris forms a temporary disk and produces a flare that rises and decays over months. The color and timing of the flare tell us how material circularizes and feeds the hole. In a few cases, a new jet appears, likely launched as magnetic fields wind up near the spinning horizon. These rare events show feeding turned on suddenly and then switched off as the debris is consumed or expelled. Gravitational waves extend the picture beyond light. When two supermassive black holes spiral together during a galaxy merger, their waves hum at very low frequencies. Arrays that time the radio pulses from millisecond pulsars are now sensitive to a background from many such pairs. The growing evidence for a common background suggests that heavy black hole binaries are common and slowly tightening across the universe. Future space-based detectors will be able to track individual spirals and mergers at these low frequencies, measure masses and spins with high precision, and test the ring-down tones of the remnant. Those tones are set by the horizon's properties. Matching them to Kerr predictions will be a direct check of the no-hair idea. Simulations bridge observation and theory. General relativistic magnetohydrodynamic codes evolve hot plasma and magnetic fields in curved spacetime. They produce synthetic images, spectra, and polarization that can be compared with data from the Event Horizon Telescope, X-ray satellites, and ground-based observatories. When simulations match many channels at once, total brightness, spectrum, polarization fraction, variability timescales, it strengthens the case that we are reading the environment correctly. Mismatches point to missing physics, such as electron heating rules, particle acceleration sites, or the role of pairs in jets. Feeding a black hole requires moving angular momentum outward on galactic scales, bars, spiral arms, and mergers push gas inward. On parsec scales, turbulence and magnetic stresses in the disk move angular momentum outward so mass can sink in. Close to the horizon, the inner edge depends on spin and sets the maximum radiative efficiency. For a non-spinning hole, the inner edge sits farther out and efficiency is lower. For a fast-spinning hole, the edge moves inward and more of the gravitational energy can be radiated before the plunge. This is why spin matters for how bright a given feeding rate can be. Jets give black holes leverage over their hosts. Close to the engine, magnetic fields anchored in the inner flow and threading the ergosphere organize plasma into a narrow beam. Farther out, internal shocks and shear light up the jet. On galaxy cluster scales, the jet inflates cavities in hot gas. The work done to blow these bubbles offsets cooling losses, preventing the gas from condensing into stars too quickly. On galaxy scales, wide-angle winds and radiation pressure can sweep out dense gas or, in some geometries, compress it and spark star formation. The net effect depends on timing and environment, but over billions of years it helps set the balance seen in galaxy populations. The biggest black holes grow by both accretion and mergers. In the young universe, bright quasars reveal long stretches of near-Eddington feeding. To reach billions of solar masses within a billion years, the starting seeds must either be heavy or the feeding must be efficient and frequent. Two paths are explored: remnants of the first, very massive stars that then accrete rapidly, and direct collapse of large, metal-poor gas clouds into black holes of 10 to the power of 4, 10 to the power of 6 solar masses that then continue to grow. Observations of faint active nuclei in early galaxies, of intermediate mass candidates in dwarfs, and of the gravitational wave background all inform which route dominated. Back in the Milky Way, the center is a laboratory at many wavelengths. Radio and sub-millimeter telescopes track flares near the last stable orbits. Infrared instruments follow star motions and find young, disk-like stellar populations that likely formed from gas that once spiraled in. X-ray and gamma-ray monitors catch brief outbursts. Together, these show a low feeding rate today, with most of the gas's heat advected inward rather than radiated away. This explains why a 4 million solar mass black hole can be dim most of the time. The push to see more continues. Adding new stations in Africa, Europe, and the Americas increases the resolution of horizon-scale imaging. Moving to shorter wavelengths reduces blurring by interstellar scattering towards Sagittarius A times and tightens the shadow's edge. Coordinated campaigns align radio, infrared, X-ray, and gamma-ray observations to follow flares across the spectrum. Time-domain surveys scan the sky for tidal disruptions and changing-look active nuclei, building large samples to study how long feeding episodes last and how they shut off. Each new method cross-checks the others. Star orbits fix mass in the Milky Way's center. The shadow size of Sagittarius A times matches that mass. Polarization near M87 times traces magnetic fields that also shape its large-scale jet. Iron line profiles and X-ray echoes in some active galaxies give spins that agree with jet power in broad terms. Pulsar timing hints at a sea of giant binaries, which galaxy surveys and merger simulations expect. None of these alone is the final word. Together, they draw a consistent picture. Horizons exist. Space-time curves as relativity predicts. Magnetic fields and plasma flows organize the energy release, and the energy released before the boundary is crossed can alter galaxies on scales far beyond the engine. The remaining gaps are clear. We need sharper horizon images to isolate the photon ring and test the metric in detail. We need long, clean records of low-frequency gravitational waves to track supermassive binaries from wide separations to coalescence. We need better models of plasma microphysics to explain how electrons are heated and accelerated near the horizon and in jets. We need larger, more complete censuses of black holes in small galaxies to understand the first seeds. Step by step, those pieces are falling into place as instruments improve and methods mature. What began as a set of equations now reads like a field guide. Mass sets the scale, spin sets the efficiency, and helps power jets. Feeding is limited by angular momentum and supply routes. Feedback returns energy to the surroundings and shapes star formation. Light bends, redshifts, and polarizes in ways that tell us about the geometry. Waves in space-time ring with tones that tell us about the horizon. Every test so far points back to the same core idea. Gravity is geometry. And near an event horizon, that geometry governs what can be seen, what can escape, and what must fall inward. We can now look at an image and know the central darkness is not just missing light. It marks a well in space-time so deep that no signal can climb out. It is a precise boundary, the point of no return, outlined by a ring of emission bent by extreme gravity. Black holes are not only endpoints that swallow matter. In the zone just outside the horizon, they can act like engines. Gas that carries angular momentum settles into an accretion disk. As it spirals inward, friction and magnetic stress heat the plasma to high temperatures. The disk shines from radio to X-rays, with a total power that can exceed the light of the entire host galaxy. The energy release is efficient because gravity does the work. Roughly a tenth of the infalling rest mass can emerge as radiation, and for fast-spinning holes, the efficiency can be several tenths. No chemical fuel or nuclear chain is needed, only a path down the gravitational well. Radiation is not the only output. Many systems launch narrow, steady jets from the inner regions. The jets are beams of magnetized plasma, accelerated to near light speed and guided along the spin axis. They carry energy and momentum much farther than the disk extends. The most widely used explanation is that magnetic fields anchored in the inner disk and threading the spinning hole extract rotational energy and channel it outward. In simple terms, the spin acts like a flywheel. The fields tap it and convert some of that stored rotational energy into bulk motion and heat far away. Over long times, this process can slowly reduce the spin, but in most real objects, the reservoir is large compared to what the jets remove. On the scale of galaxies and clusters, This output changes conditions for gas. In a galaxy nucleus, radiation pressure, winds, and jets can heat or expel gas that would otherwise cool and form stars. In clusters, jets blow bubbles in the hot intra-cluster medium. As the bubbles rise, they stir the gas and offset cooling. Without this gentle but persistent heating, we would expect more cold gas and higher star formation rates than we observe. In some regions, outflows compress clouds and trigger brief bursts of star formation. The balance between heating and compression depends on geometry, timing, and the state of the gas. Feedback is not a single on-off switch. It is a cycle. Fuel arrives, the core brightens, outflows grow, gas is heated or moved, fueling drops, the core dims, gas cools again, and the cycle restarts. On stellar scales, smaller black holes show the same physics in fast motion. In X-ray binaries, a black hole of a few solar masses feeds from a companion star. The disk brightens, the spectrum hardens, a compact jet appears, and then the system fades, all over weeks to months. Because the timescales are short, observers can watch state changes unfold and test how disk structure, magnetic fields, and jets interact. These micro-quasar episodes echo what happens in active galactic nuclei, but on a compressed clock. Because the engine sits outside the horizon, we can study it with light. Spectra from the inner disk show Doppler shifts from fast orbits and gravitational redshift from deep potential. Broad iron lines in X-rays curve into a distinctive asymmetric profile. Timing studies see lags between flashes of hard and soft X-rays as light echoes off different regions. Polarization maps reveal how the electric field vectors align, tracing magnetic geometry. In radio and submillimeter light, very long baseline interferometry resolves structures near the photon ring and measures the shadow size. Together, these data let us weigh the black hole, estimate spin in favorable cases, and test whether orbits and light paths follow the Kerr geometry predicted by general relativity. The engine can also be tapped in principle by particles and fields. The Penrose process shows that when space-time is dragged around by a spinning hole, it is possible to extract energy by splitting a particle's path in the ergosphere. In astrophysical systems, magnetic fields do the splitting and bookkeeping automatically, making a clean beam instead of a single particle trick. These ideas are not science fiction add-ons. They are direct consequences of how rotation warps space-time and how electromagnetic fields behave in conducting plasma. Black holes change their surroundings in quieter ways too. Even when feeding is weak, the central mass shapes the orbits of nearby stars. In our own galaxy, precise measurements of stellar tracks near Sagittarius A Times show a compact mass of about 4 million suns inside a region smaller than the solar system. As one star swings close, we see gravitational redshift and orbital precession, both predicted by relativity. The same data show that the central mass must be a black hole. No cluster of remnants would remain that compact and stable. In other galaxies, similar arguments based on stellar speeds, gas kinematics, or maser disks point to central masses of millions to billions of solar masses. The engine's reach goes beyond light. When two galaxies merge, their central black holes sink toward the new center and form a binary. As stars and gas extract orbital energy, the pair tightens until gravitational waves carry away the rest. The final seconds of coalescence ring with specific tones that depend only on the remnant's mass and spin, a no-hair signature of the horizon. Across the universe, Many such pairs produce a long, low hum in space-time. Timing arrays that watch millisecond pulsars are beginning to detect this background. Planned space-based detectors will, in time, follow individual binaries as they spiral and merge, giving a direct census of growth through mergers and a sharp test of strong field gravity. All of this activity takes place outside the horizon, yet the horizon is what defines a black hole. The boundary is not a material shell, it is a causal surface. Outside, some paths lead to infinity. Inside, all paths end at the singularity. The difference is not a matter of force in the familiar sense. It is the shape of space-time. Light that tries to climb out from just inside falls farther in. Light from just outside can still escape, but with a redshift that grows as the source approaches the boundary. To a far observer, an infalling clock slows and fades. To the infaller, the crossing is uneventful, and the path inward is as inevitable as the passage of time itself. These two views are consistent because they belong to different frames. Near the boundary, quantum effects enter. The curved geometry changes what different observers call vacuum. Hawking's calculation shows that black holes radiate thermally with a temperature inversely proportional to mass. For stellar and supermassive black holes, this temperature is far below the cosmic microwave background, so evaporation is negligible today. In an empty, far future universe, evaporation would matter. Isolated black holes would slowly lose mass, then end in a brief, hot phase. The link between horizon area and entropy, and between surface gravity and temperature, makes black hole mechanics look like thermodynamics. This is not a metaphor. It is a set of precise rules that match the behavior of the geometry and the fields. The unresolved part is information. If the radiation is exactly thermal, information seems lost. Quantum theory says global evolution should be unitary. Current work suggests that subtle correlations in the radiation or quantum structure near the horizon may carry the information out. Calculations in simplified models reproduce the expected page curve, where the entropy of radiation first grows and then falls. A full resolution in realistic settings remains a goal, but the direction is clear. The horizon is the meeting point of gravity and quantum physics. The singularity at the center is where classical general relativity runs out. The theory predicts infinite curvature and density when collapse passes inside a horizon. Most researchers view this as a sign that we need a quantum theory of gravity, not as a literal infinity in nature. Proposals such as loop quantum gravity and string theory offer ideas for what might replace the singularity: a finite core, a bounce, a transition to another phase of spacetime. None is confirmed. We cannot look inside. All signals from there are trapped. What we can do is test the exterior geometry ever more closely. So far, black hole shadows, stellar orbits, X-ray spectra, polarization, and gravitational waves all match the Kerr solution. If departures exist, they must be small on the scales we can probe. The point of no return has a human echo. In physics, it is a clean, calculable surface with a clear rule. Outside, escape can happen. Inside, it cannot. In life, we use the same phrase for choices that close off options. The analogy is tempting, but the science is precise. Inside a black hole, the radial direction becomes like time. You cannot choose to stop moving inward any more than you can choose to stop tomorrow from arriving. Outside, time dilation and redshift change what different observers agree has happened. This difference does not mean the event is undefined. It means simultaneity is relative in curved space-time. The boundary is not a punishment or a judgment. It is a feature of geometry produced when enough mass occupies a small enough region. If you imagine crossing a horizon, the experience depends on mass. For a very large black hole, tidal forces at the boundary can be small. The crossing would be quiet. Instruments would report normal conditions locally, even as they record that signals sent outward in never return. The view of the outside sky would contract into a bright patch behind you as light rays curve inward. The interior would not feel like a room with walls. It would feel like a one-way slope. For a small black hole, the differences in gravity across your body become large before you reach the horizon, and tidal forces tear structures apart, spaghettification well outside the boundary. In both cases, the local physics carries on according to the same laws. The global structure sets what is possible. Thinking about horizons can suggest limits more generally. There are regions of the universe that are not just hard to reach, but impossible to revisit once entered. There are questions about the interior we can pose, but cannot answer with observations from outside. This is not defeat. It is the shape of inquiry when causality and finite signal speed set the rules. We learn by gathering everything available just outside the line and by testing the governing equations wherever we can. Each check builds confidence, or better yet, exposes a small mismatch that points the way to deeper understanding. Black holes, then, are not only destinations for matter, they are laboratories. In their light we test how geometry bends paths. In their shadows we measure horizon scale. In their jets we follow how fields extract energy and move it across vast distances. In their mergers we hear space-time ring. In their slow whisper of radiation we see quantum physics touch gravity. Each strand is part of a single theme. Gravity is geometry, and geometry sets what signals can do. The image of a ring around a dark core is more than a symbol. It is a measurement, a diameter scaled by mass and distance, a brightness set by orbiting plasma, a shape influenced by spin and our line of sight. It is also a reminder that even the most extreme objects are governed by rules that we can write down and test. The horizon is a clean boundary in those rules. Outside it, we can watch matter heat, radiate, and launch flows. Inside it, the future is inward. Between them, in the thin shell, where light bends and plasma swirls, the engine runs, the galaxy responds, and the universe records the result. We end with a simple statement that ties all of this together. A black hole is a region of space-time defined by what cannot get out. The event horizon marks that definition. Everything else we observe, the bright disks, the narrow jets, the slow hum of waves, the shadows on the sky comes from just outside that boundary. There, gravity, motion, magnetism, and light act together in their most extreme forms. There, the known laws hold with impressive accuracy and also point, through their very success, to the precise places where the next answers must be found.